Okay, this is part 2 of the notes for stats. Here we go. We're picking up with the charts that we just made, talking about rejecting a hypothesis and whether that's good or bad and how that works. And we said that there's 4 scenarios, right, where your null hypothesis is true, your null hypothesis is not true, and then you can either reject or not reject each of those. And 2 of those will be the correct course of action, 2 of those will be errors. So back down to my paragraph writing here, this shows us the 2 types of errors that can be made are type 1 and type 2. We get these errors when we make the wrong decision regarding our evidence that compared the sample mean to the hypothesis mean. And like we said above, the larger the disparity between the two, the more likely we are to reject the null hypothesis. The smaller the disparity, the more likely we are to not reject the null hypothesis. This was again like that first example I did up in the top right corner here about how heartbeats per minute. If you get a sample of 83 and your null hypothesis was 82, you might not reject that. But if your sample mean was 90, your null hypothesis was 82, yeah, you're probably going to reject that. But the question is, from all that, how large of a disparity is large enough? How much is too big, or how much is not enough? When can we know for sure if we want to reject this null hypothesis? Well, that answer is going to depends on what's called the level of significance. Okay? Think of this is almost like confidence intervals that we talked about last week, except level of significance is almost like how confident are you in this thing, having an error. That's kind of like a backwards confidence interval in some ways. Maybe that makes sense, maybe it doesn't. But we use 3 common levels of significance. They are 0.10, 0.05, and 0.01. So it's 3 different levels of significance, and these represent the probability of a type 1 error. And those probabilities would be 10%, 5%, and 1%, right? That's what those decimals correspond to. Now, those are the probabilities of making a type 1 error. A type 1 error was where your null hypothesis was actually true, but you go ahead and reject it. Okay, and that's really what we can control the most here. Okay, when we make it's kind of like a false alarm. You reject when you weren't supposed to. You're supposed to let it be. And so that's what we can kind of look at here as best we can and make the right decision. So after choosing the significance level, a critical value is chosen from the z-chart. Here's what I mean by that. I'm going to draw in some stuff down here, and hopefully you guys can fit all this in. I know it's going to be a little tricky. When we're talking about critical values, it's going to have to do with your z-score, your z-chart. So you're going to have a number there, and let's say that this is one of those where you're above the line, right? This is called the critical region. Whatever is above, or it could be below, right? We talked about that before. And this is what those significance level values are: the 0.1, 0.05, or the 0.01. Those are the areas in there. And so since you are working backwards, so since you know that, the 0.1, 0.05, or 0.01, that's going to be, what this is here, that allows you to then work backwards to find your z-score. I'll say corresponding z-score. Okay? So then for each of these, there's going to be a specific z-score that tells you where you're at. Now, it's going to depend, the graph, I shouldn't say graph, the distribution is going to depend on your sign, right? Depends on greater than, less than, or the not equals to from earlier. Okay, so if it was, we said there were 3 different types. There was the two-tailed, which was when you had not equals to. And in that situation, you're going to have a little bit on the top end and a little bit on the bottom end, okay? And so you're going to have these, your distributions, you're going to have the, sorry here, I'm going to twist it around. You have 0.10, 0.05, and 0.01, okay? We represent those with the variable alpha, that lowercase a. Okay, that's gonna be the symbol you use for the probability of this type 1 error occurring. Okay, you're gonna often see that. So the probability of the error is represented by that lowercase alpha. So if a equals 0.10, then the critical value that corresponds to that, meaning what your z-score going to be, it's going to be plus or minus 1.65. Plus or minus because it's positive on the right end, negative on the left end. When alpha is 0.05, your critical values will be at plus or minus 1.96. And 0.01, your critical values plus or minus 2.58. Now, hopefully that looks familiar from confidence intervals, right? And in fact, they are the same z-score values. You think about if your critical value is 10%, 0.1, that's the same as a middle 90% confidence interval. Same thing if your critical value is 0.05, then that means that's like the middle 95% confidence interval. And then if your alpha was 0.01, that'd be the middle 99%. Okay, so the z-scores should look familiar from when we talked about that. Where they might look a little different is when we're looking at the left-tailed and right-tailed. Okay, if it's left-tailed, okay, that's where we were on the bottom end, right? We're like down here. So this would be a situation where we are less than the mean. So again, we got our 3 alpha values, 0.1, 0.05, 0.01. When alpha is 0.1, our critical value for that is negative 1.28. Notice that for all of these, the critical values are always going to just be negative, right? Because we're always below the mean. We're never going to be above the mean for our z-values. When alpha is 0.05, the critical value that corresponds to that would be negative 1.65. And when alpha is 0.01, the z-score that corresponds to that's negative 2.33. Okay. And the last one, hopefully you have room. I know I'm kind of running out of room here, is when it's right-tailed. And that would be, instead of being less than, now we are greater than. And our graph, there we go, there's our distribution. Here's the mean. So we are above. Okay, so we're looking like this. Now, alpha, 0.1, 0.05, and 0.01. So when alpha is 0.1 here, the critical value that goes with that is 1.28. When alpha is 0.05, we get 1.65. When alpha is 0.01, we get 2.33. Notice that these are just the positive values opposite from when it was left-tailed, right? And that should make sense. You know, we're only focused on one end, so it's just positive values for right-tailed, it's just negative values for left-tailed. Whereas when it was two-tailed, it's plus or minus because it can be either. Okay, so that's a big part of what we're doing here. You're finding the correct critical values. You know, being able to work backwards and find the z-score, you know, using the alpha value that's given to you. That's going to be part of the assignment. Other parts of the assignment are just understanding this concept here, knowing what it means to reject, knowing what it means to not reject, and all that sort of stuff, okay? All right, good.